Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting.
Alright, let's do this. This is our very last video for our module number 7, deep sequence modeling. So far we covered this relatively lengthier module in 4 parts and 5 lecture videos specifically. This is lecture video number 5 and that's the last one. So we covered the theory section in the first 3 parts. We started with DNN versus RNN. For time series, we talked about the data structure, how these models fundamentally treat the time series data differently. Then in part 2, we said why we should go beyond a simple DNN, and we talked about RNN specifically. But in part 3, there's a typo here, this is part 3. In part 3, we said, okay, now why should we go beyond RNN? We talked about the concept of memory and the long-term memory versus short-term memory that RNN has. Then we moved to part 4 and we did a couple of Python videos. In the past one, Python video part 1, we did univariate time series forecasting, and in this one, we're going to do multivariate time series forecasting. Awesome. Let me show you where you can find the material for this lecture video. So go to the GitHub repository for the course, then lectures and codes, module number 7, and there are 3 notebooks, right? So we covered the first one in the theory lecture. That was the intuition between DNN and RNN. And then we covered the univariate RNN and LSTM last time. And for this video, we're doing multivariate RNN and LSTM. So you have seen this example before, right? You have seen this in the theory lectures when we talked about that temperature data set. We had 14 features. And on the slides, I basically talked about all those outcomes of those models. So we started with we started from very basic. We looked into naive forecaster, then we move on to DNN, then we tried CNN, convolutional neural network. Then we move forward with RNN, and now we're doing, and obviously we finished that analysis with LSTM. And now we're seeing this thing in Python. So there shouldn't be anything surprisingly here. So you have seen all these things on the slides before. But for those of you who are curious how you can do it in Python, so this is the notebook. And this is the latest version. So the older version, there were some updates in TensorFlow that the older version of that temperature forecasting, the time series forecasting might not work in the latest version of TensorFlow. So I made some changes to that one. So make sure that your GitHub repositories are updated. And then after that, you should be able to run this model again as of today. Okay, so that was it. Let's jump into this notebook and then see the details. Okay, so the goal in this one is to replicate what we covered in the theory lectures. And basically this is a data set. Maybe we want to do temperature forecasting and using the past 5 days specifically to make a prediction for the next 24 hours. So for example, basically in the next 24 hours, right? So for example, today, at 9 a.m. the temperature is 25 Celsius. We want to see what is the temperature tomorrow, 24 hours at 9 a.m. So that's the goal. We have 14 different features, and then the target variable is temperature, and this is the data. The data goes from 2009 to 2016, and the data has been collected every 10 minutes. So we have 420,000-ish observation, and this is the data in the past 10 days. So let's go ahead and import the data set, pre-process it, and parse it, normalize it, and then basically put it into different batches, and then pass it to our network. So at the end of the day, this is what we're going to get, right? So we're going to work with a bunch of the batches of data and then pass it to the RNN. Okay, let's see how we can do it in Python. All right, so I already have it open, so it is connected to the GPU. Let's go ahead and run this. So we're going to import NumPy, pandas, matplotlib for our visualizations, especially when we want to visualize the epoch versus the performance metric and see how the model is doing through different iterations. Okay, we're going to import the data set. It's a zip file. We're going to unzip it. So let me go ahead and show you the folder. It's a light data set. It should be okay. It should be fast, right? So this is a CSV version. Actually, I went ahead and downloaded it on my local computer. I want to show it to you how it looks like. Okay, so this is the data set. We have 420,000-ish rows, and the first column is pressure. The second one is target, and it is our temperature, which is in degrees Celsius. This is our target variable, and a bunch of other features. Okay, So let's go ahead and import this data and look into that. All right, so data is there. I'm gonna go ahead and open this CSV file and read all the lines. So this is where we're going to save them, right? So lines is going to be, basically every single line of the data separated by line separator, obviously. The first index 0, the very first line is going to be our header. So if I do line 0 and split it by comma, this is comma separated, right? CSV file. This is the header, and then anything else is going to be saved in the lines. So basically, if I go back to here, this is going to be my header, and everything else is going to be the lines. All right, so we can go ahead and check out the length of the line, the header, and basically the first line. So if I run this one, it's going to show me that these are the headers, and this is the number of observations, 420,000-ish, and then this is basically observation number 1. For observation number 1, the temperature was -8 Celsius, right? This is the pressure, this is the time date. All right, so now our next job is to just basically parse it. If you want to make sure that we save the temperatures as our target variable as a different separate vector, we call it temperature, and everything else, including the temperature, we call it raw data, okay? So for example, if I look at this first line, if I split it by comma and look at the everything except the date time, so from indexing from 1, so this is how it's going to look like, right? I'm going to use this, put it in a for loop or least comprehension to extract basically the temperatures and all the values. I call it raw data. Okay, so this is what we're doing here. So temperature and raw data, let's generate some empty NumPy arrays. Basically, these are zeros. And then in a for loop, I'm going to go ahead and loop through the lines, the enumerate version. Basically, I'm going to keep track of the index and the values inside it. The values are going to be this, right, for each line. And then, so this is the values. Then if I extract the first element of the value, remember, this is the element 0, this is element first, this is it's going to be my temperature, okay? So these are going to be the temperatures. And then everything, including the temperature, I'm going to call it raw data, all right? So now we have both temperature and raw data. We can go ahead and plot the temperature. So this is the temperature over the entire years, 420,000-ish observation, right? Remember, collected every 10 minutes. And this is the temperature. If I look at the, for example, 1440, remember, where's this number coming from? It was here, 10 days, right? 10 days, 24 hours, and it was collected every 10 minutes. So we have 6 observations per hour. So it's going to be 1440. All right. So this is our 1440. Then we are going to basically decide what portion of the data should be trained, what portion validation, and what test. So we're going to go with 50% 50% train, 25% validation, and everything else, the test set, right? So simply, this should be pretty straightforward. I'll leave it up to you to just read through the code. This is pretty straightforward. We're going to end up with 210,000 train sets, 105 validation, and 105 almost test set. Okay, now it's time to prepare the data, right? So we're going to start with normalization, because remember, when you want to pass these things to a neural network, we better have normalized the data. And we are going to do simple standardization, right? So basically, we are going to work with, we are going to normalize the data using a train set, right? Because remember, we don't want to cheat. We don't want to use information from the test set to leak to the train set, or either from validation set to leak to the train set. So we're going to say that from this raw data, make sure you collect the observations in the train set, calculate the average. Okay, this is the average. We're going to demean the data, take the average out. Then we're going to calculate the standard deviation using train set, the same steps, and divided by standard deviation. So this is demeaning and divided by standard deviation. This is our normalization. Okay, the dataset has been normalized now. Now it's time to make dataset object. So if you remember from computer vision, we had this utility. It was called image datasets from array. You have the same thing for time series in Keras utils API. It's called timeseries underscore dataset from array. Basically, if you pass an array, it's gonna put it in different batches, right? So this is what we want to replicate, something like this. We want to put the data in different batches and then make a prediction in the next 24 hours. Okay, let's see how it's done. Here, actually, I'm going to show you a very simple version. Imagine I have a NumPy array between 0 and 9, so 0 and up to 9, including 9. And this is our, let's say, integer sequence, right? I'm going to go ahead and use this utility, time series data from array, and there are some stuff you can pass, right? You can say, first of all, what is the data? I'm going to say my data goes from number 0 to number 6 here, not including the last 3 observations, right? 7, 8, and 9 are excluded. So I go from 0 to 6, right? The targets start from actually the third element to the end. The sequence length, I can set it to 3, and I want to go with 2 batches, right? If I run this, let me actually show you the output, and it should be pretty straightforward to do that. Okay, so what do we have? The sequence length is 3. We have, let's say, 0, 1, 2, and then our target starts from, remember, it starts from the third one, so it's 3, and a third element, right? 0, 1, 2, 3. And then let's say this is the next sequence, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, and etc. right? And here we're just outputting 1 batch, so we know that in this input there are 2 batches of data because we said batch size is equal to 2. We can actually go ahead and check the size of check the shape of the input and target. Here, for example, I can say for inputs and targets in dummy dataset. Let's go ahead and print the input shape and also print the target shape. And of course, we need to make sure that we put a break. We don't. Okay. Okay, so our input shape is going to be 2, 3. Again, because we have 2 batches, and then for that we're going to have 2 targets, right? Okay. Now we're going to apply the same utility, time series dataset from array, to our own dataset, which has 420,000 dish observations, right? So yeah, of course, we're going to do it for train set, validation set, and test set differently. So this is what these chunks are telling us. There's nothing special here. Don't let this, sampling rate and this extra stuff distract you. Basically, at the end of the day, we want to do something like this. Give me the past 5 days, 120 observations, make a prediction for this observation number 144, which is 24 hours after this, after the sequence, right? All right. So, however, because in this special data set we're collecting information every 10 minutes, so the sampling rate is going to be 6, 6 of 10 minutes in an hour, and then we're gonna the sequence length is going to be 5 days, 120, and this is basically what we used here as number 3, right? So you want to make sure that you go all the way to the point that this is raw data, and then from that specific point make the predict. You just collect the target variables, right? So this delay is going to be equal to your sampling rate multiply sequence length plus. So this is where the next 24 hours is coming in place, right? Plus 24 and minus 1 because we have to bring back index 1. So then this basically, usually you do something like this if you want to do 24 hours from the end of the training, right? If it was 12 hours, we do 12, and we don't do this one again here just for the sake of argument, because this example was the sampling rate was 6. We had to just multiply this to make sure that the indexing is correct. Again, don't worry about it if it doesn't click, but just be aware there's nothing special here. Okay, so we're going to put them in 256 different batches. And again, we talked about it, right? 256 of these samples are shuffled and batched. So we're going to shuffle these batches, but within each batch, we're not going to shuffle, right? So within each batch, the sequence is not touched because, again, this is time series. We should reserve that time dependency. But we want to make sure that the batches themselves, between batches, we are shuffling, okay? All right, so that's what we do. We're going to say, let's go ahead and create a train dataset, validation dataset, and test dataset. So for train dataset, these are the inputs. Again, raw data. Remember, raw data included everything, including the temperature. So we go all the way except the last delay time steps, and then the temperature is from the last delay time steps forward. Sampling rate is our sampling rate. Sequence length is 120. Shuffle again is equal to true because we're shuffling between batches. Batch size is 256. Starting index from 0 and ending index go all the way up to the training index, right? So we saved it here somewhere. Yeah, this is the number of trained samples. All right, so we're gonna run this. Now we're gonna end up with 3 data sets, right? Train data set, validation data set, test data set. Each of them has 256 different batches with the length of 120, and the target variable starts from at the end of each sequence plus 24 hours. Okay, so that's it. And we can, for example, look at the raw, well, let me actually show you. We can look at the shape of one of these for the train set or test set, whatever. So we're going to look at the train data set. We have samples and targets, right? Let's look at the shape of the samples and shape of the target. So let's run this. This is exactly what I did in a couple of cells above. So again, 256 batches of data, sequence length 120, and these are 14 values, including the target variable. And target itself, of course, is going to be a vector of 256. This is a tensor rank 1, right? All right, so now our next job is to create the common sense or the machine or basically a simple benchmark, right? So a common sense here, as we talked about it in the lecture video, should be something as simple as this, random walk with no drift, maybe. What's happened today is going to be a best predictor in the next, what happened right now in this hour is going to be the best predictor in for the next 24 hours. So for example, if right now it is 10 a.m., the temperature is 10 Celsius, I'm predicting in 24 hours, the temperature is going to be 10 degrees Celsius at 10 a.m. All right, so let's go ahead and create that and then calculate the MAE in the test set and use it as a baseline, right? This is our common sense benchmark. So let's go ahead and construct that one. All right, so our common sense baseline should be pretty straightforward. This is what we talked about in the lecture videos as well. Temperature 24 hours from now is equal to temperature right now. So let's pick this temperature and label it as a predicted value, and then calculated the errors, sum those errors, and divide it by the number of observations to get the mean absolute error. Okay, let's do that. So we are going to go ahead and define our basically evaluation for a naive method. And so we're going to keep track of the total absolute error and the total sample seen. So if I take this one divided by this, it's going to give me the mean absolute error, right? So what we're going to do, we are going to work with this time series dataset object. We say for samples and targets in this dataset that we just created, and go ahead and do this. So here it says that samples, remember samples include everything, including the target variable. It says, give me everything. Remember, what was the dimension of the sample? It was 256 by 120, 14. So 256 batches, right? So say, use all the batches. Keep the last observation. See the last observation in this sequence of length 120. This is, let's say, the temperature today, right now, and we're going to use it as a prediction, right? So this is basically 1 means that go over in column index 1. So remember, index 0 was pressure, index 1 was temperature. So this is where index 1 is coming from. So this is my temperature now. So temperature in all the batches, the very last observation in the sequence in the batches, right? So that's the temperature. But we know that this has been normalized. So let's go ahead and transform it back to the regular temperature. So I need to multiply it by standard deviation and add back the average. So these are the predictions. Now I can go ahead and calculate the predictions minus targets. So y hat minus y. So these are, and take the absolute value, sum them. So this is going to be my sum of absolute errors. Now, if I go ahead and divide this by total samples seen or total number of observations, now I get the mean absolute error. So I have to keep track of those total number of observations as well. So basically, I'm going to say that, remember, shape 0 is 256, right, for the sample. So I'm going to add a bunch of those 256 to basically see what is the sample seen, total sample seen. And I'm going to go ahead and take the total absolute error divided by sample seen. This should give us the mean absolute error in the validation set and mean absolute error in the test set. So let's give it a second. It should generate these two numbers, 2.44 degrees Celsius and 2.62. Yeah, 2.44 is there, and then 2.62 is going to be generated. Okay, so now next step, let's go ahead and try our basic machine learning model. So the goal is to, as I said earlier, yeah, there we go, this is 2.62. We want to replicate these slides, right? So we're going to start with a very simple deep neural network, and then we'll try a CNN, convolutional neural network. Then we are going to see the performance of them, then move on to RNN, and then finally LSTM and bidirectional LSTM. Okay. Okay, so let's go ahead and try the very basic densely connected neural network, right? So remember we had 13 features on a target variable in the raw data. So in terms of dimensionality of the input, we have something like this. So this is going to be our neural network. The input is going to be 120 by 14, right? And obviously we need to flatten it if you want to pass it to the densely connected layers, right? So basically 120 multiplied 14, it's going to give us this basically 1680. So this is flattened now. And then we pass that one to a simple dense layer with 16 nodes and activation value. And then finally, we're going to pass it to our output layer, which is a dense layer with one node. Remember, because this is a regression, so we just need to put the activation linear, right? And then construct the model. Let's create our callback to just save this model and then call it later on. We're going to compile it using RMS prop optimizer. The loss is MSE. And the metric is MAE, because we want to just report this and compare it with our baseline common sense benchmark. Okay, we're going to run it for 10 epochs and then train a model. So I will run this. This should take relatively faster compared to RNN, LSTM, and even CNN. So I'm going to run this one only. For the rest of the notebook, I'm going to basically walk you through the outputs. But after this thing has been run, we can look at the model summary. So this is a model summary. Remember, the input shape was 120. This is a sequence length of the data and 14 features and a target variable. We flatten it. So let me actually go ahead and create a cell, show you the calculation. So 120 by 14 is going to give us this 1680. Now we have this number of units. Oh, it's waiting for the model fit. And then in the dense layer, I need to say, okay, I have 1680 multiplied by 16 node and plus 16 bias term. So this is going to be 26,896 parameters. All right, so I'm gonna let this run, but walk you through to the rest of. So as the rest of the notebook, we can go ahead and plot the validation MAE, mean absolute error versus epoch. And as you can see, basically the performance, what was the performance? We have to report those numbers, so I don't have it here. It's being generated, but we can cheat a little bit and look at the output from our theory lecture. So yeah, we will get to a test MAE of 2.62, which is pretty well. It's even let's see, it's pretty much the same as the naive forecaster. Okay, so the next one we're going to look into is our convolutional neural network. So okay, for the CNN, we are going to do it like this. So basically our input is pretty much the same. It has sequence length 120 by 14, right? And then we are going to pass our first convolutional layer, which is 1D. Again, it's not like an image that we have width and height. We have only one window, right? We're going to use 8 of those windows, and window length is 24. And we're going to slide that window through the time series. So this is pretty much analogous to what we did with the filters in image recognition. We had a 3x3, let's say, a filter, and then we slide it over the entire pixels. Here we have a window of size 24 hours basically. We're going to use 8 of those filters and then just slide it through the time series, right, sequence. And the activation ReLU, and then we're going to do max pooling after that convnet. So the convnet, max pooling, convnet, max pooling. So we're going to use the same architecture that we did in the computer vision section. And again, we have another convnet, max pooling, convnet, and then finally we're going to do a global average pooling to the entire thing. And just remember, Usually in computer vision, we increase this number of filters, right? For example, we do 8, 16, 32, and we decrease this size of the filter. Right here we have window 24, we go to 12, we go to 6. I could have gone and increased the number of filters as well. But anyways, this is what we're doing right now. And just like the other deep neural network, we're going to pass our output layer, which is a dense layer for regression. All right, we are going to go ahead and construct this model, look at the performance of the best model in the validation set, right? So again, I'm not going to run this. This is going to take some time. So each iteration, each epoch is going to take 57 seconds-ish. The first one, of course, is taking longer than the rest of them. And we get to a validation set of in a test set 3.08. So this is way worse compared to 2.62 that we had for deep neural network or the naive forecaster. So basically in this application, this CNN didn't work. I talked about the reasons why that was the case in the theory lecture. So please check out that video as well if you're interested in details. So this is the application section. We can look at the model summary. So here are the parameters. Again, we can go ahead and calculate these numbers, for example, and see how the number of parameters are calculated. For example, we know that we have 14 features. Let me actually bring a cell here. We are using a window of size 24. We are rolling it over all those 14 features. We have 8 of those filters. And then we need to go ahead and add a bias term for those 8. So if you do the math, you'll get something like this, 2,696. So this is the number of parameters in the COMNET first layer. So you can go ahead and try these things if you can, and see if you can back out these parameters. All right, that was the CNN. So we did the CNN, we did the naive forecaster, and we did the simply densely connected layers. Now it's time to construct our first recurrent baseline. So we're going to do a simple LSTM based model. So the RNN and LSTM is pretty straightforward in terms of application in TensorFlow. Let me actually go ahead and close this one. So the input layer is pretty much the same, sequence 120 by 14. Now we're going to construct our LSTM recurrent layer. So we're going to use 16 of those recurrent cells, and basically that's it. Then we haven't. So for now, let's have only one LSTM layer. We're going to stack a bunch of LSTM layers down the road to see if we can get a better performance. Let's construct the model, save the best one, and compile the model just like before. So we can go ahead and run this, and this is the output. The output is 2.56, which is a lot better compared to any of the models that we have trained so far. So not surprisingly, this is, we know that temperature is a sequential data, it's a time series, and of course an architecture that can have those properties, preserving the ordering, sharing parameters, looking into time dependencies and things like that, it's going to perform better. So no surprise here that LSTM is doing a decent job here compared to the other one. We can look at the model summary and see what is, for example, number of parameters in this LSTM layer. I can quickly do the math for you. So what do we have? Remember, the input shape was 14, and we are passing it to, we are having 16 of these neurons, LSTM neurons, right? So this is the weight for the input, right? The weight for the input. And then we have the weight for the in the actually state variable is going to be 16 by 16 because we have 16 nodes, right? And then we're going to add 16 bias terms as well, right? But this is LSTM. If this was simple RNN, that was the answer. This was the number of parameters, right? But because this is LSTM, we have 4 of those gates, right? So we have input for get, update, and the output. So I have to multiply it by 4. So if I do the math, I get this number, 1984. So this is the number of parameters that we're getting in the LSTM. Okay, so one thing that I forgot to mention is that you can obviously apply the simple RNN. So we started with the LSTM because we know that it works better, by construction. It is designed to handle longer term dependencies better than RNN. That was one of the limitations of RNN. But if you are curious to see how to do RNN, you can go ahead and try basically from the layers import the simple RNN, right? So you can do simple RNN and rerun the model and then just call it your RNN model. Okay, so if you're wondering how to do that. So that's pretty, again, implication of RNN and CNN, RNN and LSTM is pretty straightforward in Python. Now let's talk about some of the more advanced uses of recurrent neural network, right? We're going to add the dropout. We are going to look at the bidirectional, and we're going to try a stack of layers on top of each other, right? Let's do them. Let's train and evaluate a model with dropout regularized. So pretty much everything is the same. I'm going to go ahead and increase the number of recurrent cells that I use, because now we are adding this dropout. So we can basically less concerned with overfitting, so we can increase this number of recurrent cells. There are two types of dropouts that as we talked about in the lecture video. One is a dropout for the recurrent, we call it recurrent dropout. And in those ones, the key term was that we should use the same pattern at every time steps, right? So here there's no randomization. We need to make sure that we're doing it correctly. However, in the ordinary dropout, we can do basically randomly switching on and off these nodes, right? All right, then the rest is pretty much the same. So nothing new here. We just added this recurrent dropout into our recurrent network, recurrent cell, right? So let's go ahead and run this, then train the model. As you can see, this is taking a lot longer, 372 seconds compared to the previous ones, right? The one with the dropout is going to take a lot longer. And we can go ahead and look at the performance of that one. I think, well, I have to let it run, so I'm not going to do it here because it's going to take some time, but let me actually show you what was the performance. So with the dropout, the performance was 2.45, which was a lot better compared to even the simple LSTM. But one problem with the dropout was, if you look at the validation versus train MAE, surprisingly, the validation MAE is better than train MAE. So that's a sign that your model in the train set is oversimple, right? So maybe this we are overkilling it by using this large ratio of dropout, or this 1.25%. So we have to go ahead and fix that. So how do we fix that? By making the model more complex. How do we make the model more complex? By stacking multiple layers. So let's go ahead and do that. So I'm going to go ahead and stack a bunch of those layers, but here instead of LSTM, we're going to use GRU, right? So now I use a couple of GRU layers, and again, 32 nodes. Recurrent dropout, we can do 50%, 50%, because we are making the model flexible enough, complex enough. So hopefully in the train set, the performance is going to be better compared to validation set. And that's pretty much the case. So we're going to rerun this thing and see how it's performed. Again, I have to, you can go ahead and try these things on your own, but because here, just for the sake of visualization, I use the slides from the lecture video, because each of them is going to take, look at that, 670 seconds, right? So if you stack layers with basically the bunch of GRU layers, we get to something like this, right? So obviously we get to a point that the train MAE, of course, is better than validation. The train at this point, the model is flexible enough, it's better than validation. And overall, we are doing an okay job, except for the fact that right off the bat, this thing is overfitting, right? So we have to fight that overfitting as well. Yeah, that was the model with stacking recurrent layers. And then finally, we are going to look at bidirectional ones, right? So in the theory lecture, we talked about the bidirectional RNN. We basically discussed that we're gonna pass the data basically chronologically and anti-chronologically. And the hope is to capture some patterns, some representation that might be overlooked by unidirectional RNN. So that's what we did in the theory lecture. In terms of application, again, it's super easy. We don't touch anything in the model, just we are playing around with the layers in between. Now, instead of basically LSTM, we are applying bidirectional to a bunch of LSTM recurrent networks, recurrent cells, right? So that's it. We can stack a bunch of these things if you want, but here, just for an example, we're doing it the simpler version. This is a simple bidirectional LSTM, which happens to be the state-of-the-art model for a couple of years at least, especially when it comes to text analysis. Yeah, we can run this model and we can look at the outputs. It seems that the test MAE is 2.76, which is not an improvement on our previous models, which was stacking GRUs, which was 2.39. And we talked about it in a lecture video as well, why this didn't work for our time series data, because in the time series data, in the like temperature, we don't need to look into antichronologically sequence in the data, right? So that doesn't make any sense. However, for text analysis, this bidirectional RNNs are gonna perform better compared to unidirectional RNNs. All right, that was pretty much it. So I tried to keep this Python video short. I assume that you have watched the lecture videos first. No, you have to watch them together. Otherwise, it seems that it was kind of fast. Okay, so one very last thing that I wanted to say is that, for example, how you can replicate these things, right? And these epochs versus training and validation MAE. Once your model has been trained, imagine you're doing this one. You're doing bidirectional LSTM. Once the model has been trained, you can go ahead and look at the model look at the history. And in that history, you can get access to the MAEs, and of course, you can plot it then. So basically, you have to just use these things that we did at the beginning, right? So here, so you can go ahead and create your loss object. No, this is your MAE. Validation loss, this is val MAE. So these are what has been already saved in the model history. And then you can go ahead and do these plots. So we have done these things a lot before, so that's why I just wanted to abstract from these things again one more time and keep this video short. Okay, that was pretty much it. So before I wrap up this lecture video, let me quickly remind you that please make sure you work with the latest version of these notebooks on my GitHub repository. So this one, depending on when you're watching this video, it might be different from what you saw in this lecture video. Okay, so make sure you update your repositories, and then, for example, go to this one, and as you can see, the latest version of TensorFlow is 2.17. Now it's not 2.11. And again, there were the few more changes that I needed to make to the notebook to make sure that it's running. So the original version is not running anymore because, as I said at the beginning of this lecture video, the Keras made some updates that you need to take care of those things. So if you scroll down, again, make sure that you see you are paying attention to those changes. But the point is that all these notebooks that are on my GitHub repositories, no matter when you're using them, they should be up and running because I keep updating them very frequently. Okay. So that was pretty much it. So until the next one, take care.
If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background on econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.